Find a formula for the Riemann sum obtained by dividing the closed interval into n equal parts and using the right-hand endpoint for each x sub k. Find the area by then taking the limit as n approaches infinity. And here we have the function f of x is equal to 2x cubed on the closed interval where x is greater than or equal to 0, less than or equal to 1. So to get us started, we are letting n be equal to the number of subintervals. And we also are going to go ahead here and let our interval from x0 to xn be defined as what's given, 0 to 1. So we can compute the width that will confirm with our kth subinterval. So we have delta x, and we can know that this is the length of that interval x sub n minus x0 all over the number of subintervals with n. So this is 1 minus 0 over n, which leaves us with 1 over n. So we're going to keep this in mind. We want our width to be 1 by n, and we are going to confirm this by taking the width of that kth subinterval. So that being said, let's find those subintervals. So looking at our given interval here, we're starting at the endpoint 0. So our first subinterval will be 0, and then we again think to ourselves, all right, 0 plus the width, so that's 0 plus 1 over n, which gives us 1 over n. So then our next subinterval starts at the previous subinterval's endpoint, and then we think to ourselves, 1nth plus 1 over n gives us 2 over n. And we can do this again, right? We have 2 over n, and we think 2 over n plus 1 over n gives us 3 over n. And we continue merrily in this process, and we get up to our kth subinterval. So in order to help us find that kth subinterval, look back at the previous intervals. So look at our second interval here. We have 1 over n to 2 over n. In the third interval, we have 2 over n to 3 over n. So in our kth subinterval, we're going to have 1 less than k over n to k over n, or k minus 1 over n to k over n. And we continue all the way to the very end where we have n minus 1 over n to n over n, which we of course realize simplifies to 1, which is what we were hoping to find, right? This confirms that right-hand endpoint of our given interval. And so again, the most important subinterval here is our kth subinterval. We're now going to use this to verify our width and to find the height. So give ourselves more room. So we are going to use the kth subinterval to find the width and height. So we're finding delta x sub k and f of x sub k. So we'll start with our width here. So we know that the width in the kth subinterval should just be the difference of the endpoints. So x sub k minus x sub k minus 1. Excuse me. Plugging in those endpoints, I have k divided by n minus k minus 1 divided by n. And we have a common denominator here, so that's just going to be k minus 1 all over n. And if we go ahead now and distribute this negative through, we can see some nice simplification. We have k minus k, negative times a negative gives us plus 1 over n. And those k's cancel each other out to 0, leaving us with 1 over n. So we've confirmed that the width in that kth subinterval is still going to be 1 over n. And now let's go ahead and we'll find the height. So f of x sub k, And let's keep in mind here that x sub k is this k by n. So we're evaluating our function at k divided by n. So this is going to be 2 multiplied by k divided by n cubed, which is 2 times k cubed, all divided by n cubed. So we have the width and we have the height. And we're ready now to find the Riemann's sum, or to find the formula for Riemann's sum. We want to find the formula for Riemann's sum so that we can take the limit and find the exact area. So we know that the area is approximately equal to the finite sum from k is 1 to n of the height in the kth subinterval multiplied by the width in the kth subinterval. So this is going to be the sum from k is 1 to n of the height that we just found. So we have 2 times k cubed divided by n cubed. And this height is multiplied by the width, which is 1 over n. So let's simplify. This is equal to the sum from k equals 1 to n. Now keep in mind here that the variable is k. That variable in our general formula is k. Everything else is a constant. So I'm going to rewrite this as 2 divided by n to the 4th. Those are constants multiplied by k cubed. So thinking back to the algebraic properties of finite sums, we can pull that constant 2 divided by n to the 4th out in front of our summation. So I have 2 by n to the 4 multiplied by the sum from k is 1 to the nth of k cubed. And we're excited. We realize, hey, this is the sum of the first n cubes. That's one of those general formulas. So I can rewrite this as 2 divided by n to the 4th. And this is now multiplied by, we rewrite this as the sum of the first n cubes. So sum of the first n cubes. And it's a direct formula here. So it's going to be n times n plus 1, all divided by 2, and that is squared. So we can simplify now. This is going to be 2, all divided by n to the 4th, and I'll distribute that square through. So this is going to be multiplied by n squared times n plus 1 squared, all divided by 2 squared, which gives us 4, and we can simplify. So we know, of course, 2 goes into 4 2 times, and the n squared will cancel with 2 of those n's in the denominator. And so this is leaving us with, so I have 1 over 2n squared. And now we can go ahead and we'll expand this binomial product. So I have n plus 1 times n plus 1, which gives us n squared plus 2n plus 1. And again, keep in mind here, we know we want to take the limit. So I'll leave this constant 1/2 on the outside, and we'll distribute 1 over n through to each term of our quadratic. So this will be n squared by n squared plus 2n divided by n squared plus 1 over n squared. And this simplifies to 1/2 multiplied by 1 plus 2 over n plus 1 over n squared. And we have set this up beautifully now to go ahead and take the limit. So this is the formula for Riemann's sum, simplified. And we're ready to apply that limiting process to get the exact area. So we can say, by Riemann's limiting process, again, we know that if we take the limit of our Riemann sum, the sum from k is 1 to n of the height in that kth subinterval multiplied by the width in our kth subinterval. We're taking this limit as n is approaching infinity. That gives us the exact area. So plugging in what we just found, we have the limit as n approaches infinity of 1/2 multiplied by 1 plus 2 over n plus 1 over n squared. And we can see that all of those reciprocals, this 2 over n, right? That's going to approach 2 over infinity, which goes to 0. Same thing with this 1 over n squared. That's going to be 1 over infinity squared, which goes to 0. So we're just left with 1/2. A limit of a constant is just that constant. So we have 1/2 times 1 for a beautiful final answer of 1/2. And just don't forget, this is the area. This is the exact value of our area by Riemann's limiting process.